Hello, my name is Casper and I'm going to tell you about my project called Mapping Google TensorFlow Neural Network Classifiers on FPGAs, which is supervised by Dr. Dirk Koch. Since my project isn't very interactable, I'll spend more time explaining the project first. Now, what does this long title mean? Let's try and break it down. The project is about creating a tool which processes a neural network which consists of a lot of nodes passing information forward based on its inputs as shown on the image. In order to create these neural networks, a lot of different platforms have become available, and one of them is the open source platform made by Google called TensorFlow. Then, we take the TensorFlow neural network and map it on an FPGA chip, which is basically programmable hardware. Now, let's have a look closer at the different subjects. Neural networks is a popular machine learning field which helps with different classification or regression problems. On the screen, you can see a classical simple multi-layer perceptron. It has an input layer, hidden layers, and an output layer, which all consist of nodes calculating with weighted inputs and forwarding the results to the next layer. There's a lot of research based on these networks nowadays because there are a lot of countless ways to configure these for different problems. The easiest example is to simply ask, how many nodes or layers should there be? There are also two phases to working with neural networks. One of them is training and the other one is inference. With this project, we're only concerned about the inference process. Now, I'll explain how a tool was created to automatically generate these models on custom hardware configurations. First, on software side, TensorFlow has gotten really popular and has had a lot of community involvement, and therefore it consists of many different parts as seen from the image in the middle. One example is the Keras platform, which is a higher abstraction level tool built on top of TensorFlow. For this project, it was decided that the input model has to be a Keras model, since that suits better for this tool. So the tool takes the Keras model and analyzes its topology and gets something similar shown on the screen. That doesn't look anything too complicated, but the models could also have hundreds of nodes in a layer. Then having that many connections in hardware isn't good, and that is called having a high fanout. The solution is to change the data path to be serialized. Each node just gets data from the previous node and forwards the results forward. Each node has its own weights, and based on the index of the input it does the necessary calculations while passing the results forward and forwarding its own results as well when possible. Here we can see a simplified schematic of a processing element which has 4 inputs and 4 outputs and is passing data every clock cycle. With this design we can scale the neural network however we want. Then there is a last big hurdle left. Floating point arithmetic takes a lot of space in hardware, and since we'd like to save as much space as possible on FPGAs to be able to fit big models on them, we need to quantize all of the data to reduce the size of the model and to be able to do only integers calculations. So in order to quantize the data, we need to use the equation shown. This way we can represent any floating point number as 3 integers. Next, we can see what kind of calculations are done in a node. It is just multiplications and additions. If we combine the first 2 equations, we can see from the third equation how integer-only arithmetic is possible in this scenario, and that is how the tool processes the data as well. Now, let's see how the tool works in action. Here we have opened the terminal screen showing the necessary files to run the tool and an additional Python script to create the model first. As you can see, we create a simple fully connected network with 100 nodes in the first hidden layer and then 10 in the second and 10 in the output layer to classify MNIST database handwritten digits. We save the model to a keras model.h5 file, and we also save 1000 test images for quantization. Now, if we run the script, you saw an example of how the input looks like. We can see this simple network trained for 4 epochs over 60,000 images, and then in the end we can see that it achieves a 92% accuracy. This is just an example of what kind of input model is required for the tool. We can see that the model and the data files have been created. Next, we'll be running the tool, passing it freshly made files. It will then process these as described earlier, and will output hardware description language code written in Verilog, which we can use to configure our FPGA chips to classify handwritten digits just as this model could. As you can see from the opened up file, there are a lot of processing elements instantiated with the required parameters to run this model. You can also notice all the quantized weight values being represented with 8 bits in this case. Now, finally, let's see what kind of Verilog code did the tool produce. Here we have Vivado open, showing the output from the tool. The code has been packaged into a module to easily place it in that created test bench. In the test bench open now, you can see the module instantiated with the required input and output. Now, if we run this test bench simulation, we will be feeding the module pixel data one by one from 10 different images. These images are of the 10 digits in order. The simulation will run the data through the module and see if it recognizes these images correctly. We can now see that the test was successful, and we can look at the resulting waveform a little bit closer. If we look at the classification data from the module, we can see that indeed the first image was of the number 0, and the second one was 1, and the third one was 2, and so on. Next up, I'll close the simulation and show you the resulting schematic and synthesis results, since I did those earlier for this module. All in all, the tool created with this project achieved its goals and does help automatically generate FPGA designs based on input TensorFlow neural networks. Because of the complexity of the subject, more tools like this are required. And thank you for listening.